needed for a single rotation of the rotor, and so of the alpha plate. Then we have a relative encoder that is composed by 64 slots. And as before, we read the time at the beginning of each slot. And so the delta Ti, so we have delta T1, delta T2, up to delta T64. Each delta T is the time needed from the beginning of one slot to the beginning of the following one. In our system, we were able also to read the crossing time of each slot, but at the moment we are not using this information for the angular reconstruction template. If we analyze so we took data for a lot of time, and if we analyze the distribution of the delta Ti as a function of time, we expect to have a Gaussian distribution for each delta T, and this is what we found. So we mainly have a Gaussian distribution for all the slots, and the width, so the standard deviation of each Gaussian distribution, is related to the motor instabilities, or is induced by the noise of our system. And also we expect that this distribution should be centered in 0, but this is not true for all holes. And this is probably induced by the phase of the motor, or by positioning error of the holes, of the slots. I mean, from the machining point of view. If we take the standard deviation of each of these Gaussian distributions, we can see that there isn't an evidence of correlation with the motor phase. So this is a good news. And for the standard evaluation of the angle reconstruction capability, we can take an average of this value. So we have a mean value of the standard deviation, and this value is related to the error we have expressed in arc minutes. And so for this system, for our system, we found that the angular accuracy is on the order of 0.1 arc minute. That is a very good result. But we notice that our resolution is not limited by the resolution, the readout time resolution of our system, that is on the order of 2 microseconds. And so 2 microseconds corresponds to an angular accuracy mainly 1 order of magnitude lower than the one we measured. So this black line in this plot. So so when we notice this, we notice that probably we have more noise in our system than we expected, and this is very common in this kind of system. So if we analyze, for example, a stream of data, first of all, we notice that we have an instability, or a long-term instability, that is on the order of 1.5%. This is the angular velocity of our system as a function of time, and these are a lot of minutes. But if we take a shorter stream of data, for example, of 5 minutes, we notice that the instability is lower, so it's on the order of 0.3%. And this is the same if we take a shorter stream of data. These are a few seconds. So as you can see in this plot, we have this is mainly this is noise. This is readout noise, and so what we did is to take a very short stream of data on the order of 1 second. So it means one rotation of the system, and if we analyzed the angular velocity variation from one slot to the following one, this variation is on the order of 0.01 radians per second. And the question is this variation physical or fictional? So induced by noise or physical of our system? To answer to this question, we perform a very simple calculation. We wrote the equation of motion of our system. So we have the torque induced by the electromagnetic force by the coils, and the torque induced by the friction. We know how much is the friction because we measured it. And so if we neglect one of these two terms, we have an upper limit of how much could be the angular velocity variation from one slot to the following one. This is only due to the inertia of our system. So this is the most pessimistic case. And we found a value that is 2 orders of magnitude lower than the one we see in our data. So this is the main reason why we decided to implement an algorithm, a filter, to remove the noise in our data. The idea is to implement a Kalman filter. A Kalman filter is a very common filter in systems like this one. So a system where we try to measure, for example, the position and the velocity of a system. So this is used in, for example, in the spacecraft, in the attitude control of the spacecraft, and so on. The idea of the system, of the filter, is to combine the physical properties of the system with the measurements performed. So in this way, we can, if we know the physical properties of the system, after we can measure a quantity of our system, for example, the velocity, then we can make a prediction of the next measurement. So we can, based on this prediction, is based on the properties, on the physical properties of the system. In our case, is mainly based on the inertia of the system. Then we can make the measurement, and so we can correct the measurement by comparing the prediction and the measurement and the last measurement, and so we can moving on. The most important point of this filter is that if we have a Gaussian noise, and this is the noise we observed and we saw before, the Kalman filter is the optimal estimator for the right parameters of our system. This is the main reason we decided to use this filter. To implement this filter, so we need a dynamical model of our system, but the dynamical model is very simple. So we have, as I shown before, we have the electromagnetic force, and so the electromagnetic torque and the friction torque. And when the system is stable, the angular velocity variation, so the acceleration, is approximately 0. So these two contributions are approximately equal. So we have that the variation of the angular velocity should be normally distributed with a standard deviation that we can estimate from the variation of the current we induced in the coils. And so by solving this very simple equation, we have the equations of motion. We can also discretize this equation, and we can write this equation in a more compact way. But this is not important at the moment. So what we did with Kalman filter is to, as I said before, is to predict the state of the variables we are analyzing. So we make a prediction. We make a prediction of the covariance matrix, that is the other important parameters. And after this prediction, we measured the new variables of our system. We can compare the predicted variables with the measured variables, and thanks to a Kalman gain, that is a parameter related to the physical properties of the system and related to the covariance matrix of our system, we can update, we can make a new estimation of our quantities, of our variables, and also of the covariance matrix. And the only input parameters we need is the initial parameters, so the initial velocities, the initial velocity, angular velocities, and its error. And we have these quantities, and also the error on the data we take. And the error of the data we take is related to the standard deviation of the distributions we saw before. And so thanks to this filter, we can improve the estimation of, for example, of the angular velocity of our system. So in this plot, you can see in red the measured value of the angular velocity that are very noisy, and in blue you can see the updated values of the angular velocity with the relative error bars. And if we zoom in a very small region of this plot, so a region of 1 second, like the one I showed before, we can see that the variation of the updated values in this very short interval of time is lower than the upper limit we estimated from physical considerations of our system. So this new estimation is consistent with what we expected from a physical point of view of our system. And so, just to conclude, we developed our system. Our system is mainly based on a PID controller that was used to stabilize the rotation, and thanks to this PID controller, we can obtain an angular resolution of the order of 0.1 arc-minute. That is a very good result. But by introducing a Kalman filter algorithm, we can improve this angular resolution up to a factor 6 or 7. So moving from 0.1 arc-minute close to 0.01 arc-minute. At the moment, we have already planned further iteration on this development. The first one is to use a new template which takes into account, which uses the data of the crossing time of the single holes that we didn't use at the moment. Then we are planning to improve the stability of our system. So the long time stability of our system, this will be done by improving the readout time resolution, and in particular by improving the digital to analog converter resolution used to control the current, the magnitude of the current in the coils. And finally, we are planning to improve the feedback, and this will be done by adding a Kalman filter algorithm online in addition to the PID controller. So this version of the Kalman filter probably will be a simplified Kalman filter, but should help us to give a more accurate feedback to the rotor, so during the rotation. And so I have concluded. If you have questions.
Thank you very much, Fabio. This is a very interesting and probably a bit hard to digest topic. And the improvement seems spectacular in your plot, your timeline plot. So I don't know if there is any question. I actually have a question to start with. So I guess this Kalman filter is applied somehow in a post-processing phase. Have you considered the application before the feedback, the PID feedback? Do you think this is can give any improvement to the feedback, or it's just negligible effect at the feedback level?
No, at the moment the filter is implemented a posteriori. But
yeah, because at the moment the feedback is on your noisy stream, right?
Yes, right. But
in your blue stream. So I wonder if you think you need to filter somehow, maybe not with a Kalman filter, but with some other filter your time stream, or the PID is by himself filtering the noisy stream.
Yeah, no, this is what I was referring to when I said we are planning to implement a simplified Kalman filter. So this, yeah, please go on.
No, go ahead. So you're trying to do that. You think you can have some improvement this way?
Yeah, I think yes. I think it's it will be also important to implement a Kalman filter in the analysis of the data. But if you can filter the data online, you can give a more accurate feedback, and so this feedback could help in the stability of the rotation.
Okay.
We have not tested yet, but this is this
so
is
you
the
need
idea.
You need to include the Kalman filter into your Arduino code.
Yes,
basically. Okay, is there any other question?
Can I have a question?
Sure.
Oh yeah, this is Hiroka speaking. Thank you very much for a great talk. About the Kalman filter, I think you assume the noise is white. That means that there's no correlation. So that the Kalman filter is working correctly, I guess. But if we have somehow correlated noise, I guess the Kalman filter not work properly. So the question is how you are sure you can make sure that you have some uncorrelated noise in your system. And then what happens when we have some bandwidth noise on the measurement of the position of half-wave plane?
at the moment we assumed uncorrelated noise of the data.
Yeah.
I honestly I don't know what expected.
Okay. Yeah. Right. Yeah. That's what I want to know. Right.
I think that in this case, if there is some correlated noise, the Kalman filter may lose some part of his. I mean, can provide a little bit of biased result, but we'll see how much this is biasing the result, and probably it's in any case an improvement with respect to the no filter options that Fabio was showing before. So yeah, maybe not as optimal as in the case of uncorrelated noise, but still there is a large improvement, and maybe we can estimate the level of bias induced by the correlation, but I guess it's probably a small one.
Okay, thank you, Rich.
Okay, if there are no other questions, we can. So in principle, we wanted to have a final discussion. We are a bit late now, and the idea was to discuss how to, organize the work of the work package. I don't know if Sophie, no, she's not connected. So I think we have seen very interesting inputs, and there are, this is, as I said at the beginning, we just covered a few aspects related to the output plate, and while the work package is supposed to cover many different aspects like noise, electronics, detectors, optics, so it's a very wide topic. And so what I wonder is how we can, get organized in terms of, the travels that this program supports with, having the work done. And, so I don't know if we can discuss that in detail now, but I guess the point is that we should all think of looking at the kind of work that has to be done, how this work can benefit from travels from Europe abroad, and which kind of collaborations we can do in order to improve the work package activities. And I think this is a general point about the project, and maybe we will discuss after the general end of the kickoff series of meetings. I don't know, Guillaume, if you have any comments.
No, I agree with you. I think it's maybe a bit premature to make accurate plans, but the presentation we have seen today are really a good starting point to me in many aspects. I mean, since the project is financing travel from Europe to abroad institutions, I think it's good to think in a way of a collaboration between groups. Like, for example, if I take John's work as an example, there is nice work which is done there, and there is nice work which is done in Japan, as was presented by Yota, and I think we should think of trying to find synergies between the two works. I mean, this is an example, but and I can see that there is a lot of paths in what John presented to, like, for example, incorporate some half-wave plane modeling, or also see how we can model the beam shapes, the different terms, etc. So yeah, I don't know if people have comment on that. John, if you want to say, I don't know if John is connected, by the way. Yeah.
I'm here.
Yeah.
Yeah, I agree. It's absolutely synergies and expertise that can be combined to get a better product for sure. Yeah.
Okay, I think we have passed the time. Maybe we can close. I don't know if you want to have a final word, Guillaume, and remind us the next appointment.
Right. So one thing that that would be nice is to speakers, if you can provide your presentation to me and Trong, we will put on the web, if you don't mind. So I think so that people can look the presentations after. And we will put the videos also.
Yeah, yeah. What do you want to do with the video? It will be on the cloud for I guess 1 month, but you can download it and okay, I'll send you the details.
It's possible to download it, you say? Or...
I think so. I can download it for sure. So I
okay,
can.
okay. Yeah, so we will put a link, provide a link on the. I think it's the best way. Provide a link on the website so that people can watch. Some people asked me already for the first day, so I think it's very useful to have those videos. And then the next session will be Work Package 2, led by Paolo Natoli and Mathieu Tristram. It will be next week. Which day did we say already? Sorry, I should have prepared
next Monday, right?
Yeah.
At 2 UTC, 2 p.m. UTC.
2 p.m. UTC. Okay, and then after that we will change time zone so that it's easier for other people to attend. So, but we will remind all that. Thanks a lot thanks Francesco for this session. It was very nice. Thanks to the speakers also.
Yeah, I would like to thank the speakers because I think the quality was very, very high.
Yeah.
Thank you very much. Okay.
Thank you.
See you next time.
See you next time.
Bye, everyone.
Thanks.
Ciao.
Bye.
Bye.